Yes.
Okay, so the live stream has started. We are live on YouTube now. I just want to make sure that whatever I'm talking is sort of audible on YouTube.
Go out and hear.
Okay, so
You
the live stream
someone
is
who's watching on YouTube has to hear the voice out.
What's the problem? Oh, right. Okay. Yeah.
So we can start now. Can you hear me online? Who's online?
Yes, yes.
Can you hear me?
Yes.
Oh, okay, fine. So we'll start. So it's my pleasure to introduce Professor Raymond Bishop from the University of Manchester. And he's also a distinguished visiting professor at our center. Some of you may have met him last year, so you're happy that he's visiting us again. Professor Bishop is one of the best known quantum many-body theorists in the world today, and he has contributed a number of problems in quantum many-body theory, particularly using the coupled cluster method. He is a recipient of the premier international award in the field of quantum many-body theory, that is the Feinberg Prize. And he has been very active in promoting quantum many-body theory internationally, and was one of the founders of the series called Recent Progress in Many-Body Theory. And we're happy that he's visiting us. I mean, and we have benefited a lot from him last year, and I'm sure all of you will benefit. And so I encourage all of you to have discussions with him, and he'll be very willing to interact with you. Okay. So with these few words, let me welcome Professor Bishop and request him to give us.
Thank you very much, Banu, for those kind and fulsome words. As Banu said, last year I was here and gave 3 talks on coupled cluster theory, and I thought this year I would change the subject seemingly entirely at first, but in reality it really isn't entirely, as you will see. Although my main field has been in quantum many-body theory for a large number of years, larger than I care to remember these days, I have had a long-standing interest in quantum optics and related methodology, which goes by the title, broadly speaking, of quantum phase space techniques. And what I'd like to do in the 3 lectures, today, tomorrow, and Friday, is to give you a flavor of why quantum phase space technology is both interesting and important, how it can give new insights, in particular, new insights into old problems, and in particular, how using its methodology, one can wander off into totally new directions, which have hitherto not been seen at all. So today, and I should say, perhaps apologetically, but I think not, that these 3 lectures are really geared to novices, in particular to students. Some of you may know many of the things that I'm talking about today. I suspect none of you will know everything. So what I want to do today is to lay the groundwork. So it's journeys to quantum phase space. And then tomorrow and Friday, I want to, so we have a common groundwork on which we can establish today. And then on tomorrow and Friday, I would like to go see how this groundwork that we've laid can then be used to wander off into new and productive directions. So the format of today's talk, and by the way, I should say where I stop today is not. I've got 3 talks, and I will cover them all. But where the stopping point is today is not particularly important, because I would really like to be questioned if you have any questions, and I don't like saving questions up to the end. So if you have questions, ask as we go along. And it really doesn't matter if that slows me down, because I will just pick up where I left off tomorrow, and we will cover the material regardless. So I hope that's okay with you. So I want to set to introduce why these, in the next one slide, why this technology might be important. And then to set out the basis. Almost everything I'm talking about today is known, but it's not all known to the same community, and it's not all being gathered together in perhaps a way that I will present today. And then at the end, I will give you a discussion about what we've spoken about and how it might lead on. So the introduction really is that quantum phase space techniques provide the theorist with a very powerful toolbox in areas such as quantum optics, and increasingly, and that's why I think it's important here, for quantum information processing. The In particular, the other fields are things like atom-like interactions, Bose-Einstein condensates, condensed matter physics has picked it up enormously. Very interesting areas like things involving quantum maps and quantum chaos. Very interestingly, a lot of this stuff is of great use and has sometimes been independently reinvented in signals processing. And you wonder why. That's got nothing to do with quantum mechanics, except at the very heart of it is an uncertainty principle. And it's the uncertainty principle that goes with Fourier transforms, basically. You have an X and a P operator, even though they're not quantum mechanical. And many other areas of mathematical physics. So the aims today are to lay and explore the foundations of quantum phase-space technology. I want to give you an appreciation of its strengths and freedoms to extend our understanding of quantum systems. And so, as I said, today I would like to take these first steps in getting there, and then in the latter two talks to start to explore the territory. So let's start very, very simply. Let's start with a particle traveling in one direction, let's say the x-axis, the infinite x-axis. Position operator x hat and momentum operator p hat, and I'm going to try today, I might miss somewhere in here, but I'm going to try to put hats on all of the operators. I won't necessarily do that tomorrow and Friday, but let's do it today. So all we require is that x hat and p hat satisfy the usual commutation relation. Formally, this is just the simplest of the Heisenberg-Weyl algebras. Three operators, x hat, p hat, and the unit operator that form a closed algebra. It's the simplest of all possible algebras, the simplest of all possible groups. So let's say that these, just to set the terminology, the x hat operator has eigenstates x0, and because I'm going to be using p eigenstates and x eigenstates, and if I don't label them, they can become very mixed up. I will put an x suffix and a p suffix to indicate this is an x eigenstate and a p eigenstate. Normalizations implied by the completeness relation, so I'm going to assume that the x states and the p states are complete. It's not an assumption, they are. And the metric I'm going to take is 1 in both cases. So this is integral over dx, integral over dp. That implies the normalization that there's a 1 upon root 2, 1 upon root 2 pi. This is the mathematical convention. Tomorrow I will actually adopt a different convention. I'll adopt the physicists' convention, which says this is how x states are normalized, but p states get a 1 upon 2 pi in them. And then that 1 upon root 2 pi disappears. This is just normalization. But you have to be very aware of these facts because small facts rapidly pile up and lead to errors, and factors of 2 pi are immensely important in this stuff. So get it right from the beginning. Now we can map, if we want, onto the linear harmonic oscillator by defining destruction and creation operators in the usual fashion. And then just by using the so linear combinations, the destruction operator, it's not obvious why it's a destruction operator yet, but the destruction operator is basically x plus IP and its Hermitian counterpart x minus IP. These are the factors put in so that the commutation relation between A and A dagger is 1, the unit operator. Henceforth, I'm going to put m equals omega equals h bar equals 1 almost everywhere, or I will put factors of h bar back sometimes when they're important. We can map this onto a single mode of the electromagnetic field if we're doing quantum optics, simply by replacing m goes to h bar omega over c squared. The harmonic oscillator Hamiltonian in the way with the factors that I've just put in, half omega squared x squared plus a half mv squared p squared upon 2m, then maps to this in the usual fashion. So the eigenstates of this says it doesn't matter. We don't have to have a harmonic oscillator. This is just a mapping if we want to use it. All we really have is a particle moving on the real line. But this enables me to to define some new operators. We don't necessarily have to have this Hamiltonian, but it's an interesting Hamiltonian because the eigenstates of this are the usual orthonormal set of number states. So it's just a way of introducing the number states, okay? I'm going to put a suffix n here to indicate this is a number state, right? We've got x, p, and n, so we better not mix them all up because they've all got Latin, they're all part of the Roman alphabet. And it's very easy to see that the number eigenstates are, this is the vacuum, and we let a dagger act n times. So basically, a dagger is a step up operator. One operation takes you to n equals 1, n equals 2, n equals 3, and a is a step down operator. And this is just the normalization factor. So the vacuum state is defined as usual by, if you let A act on it, you get 0, because there's no state with fewer than 0 states. Okay, so that's the definition of the vacuum. With that definition, it's relatively easy, and I haven't put a suffix 0 on here because the vacuum is the vacuum is the vacuum. It's the vacuum for everything. There is only one vacuum. So I don't have to. It's easy to see that its X representation is a Gaussian in X space, and its P representation is a Gaussian in P space. They're complete, and they form a resolution of the identity operator. So nothing fancy here. This is still perhaps not quantum mechanics 101, but it's quantum mechanics 201 or something, right? Now let's introduce what's not in quantum mechanics 201. Let's introduce the Glauber coherence states, which are defined to be the eigenstates of this operator, A. Clearly the vacuum is one of them, but what are the others? And I have to be careful now, because A is not a Hermitian operator. So its right and left eigenstates won't be Hermitian counterparts of each other. So I'm interested in the right eigenstates. So what I want is a state that I'm going to call Z. Now, I don't give this any suffix because these are the main states that I'm going to be talking about. So if it doesn't have a suffix, it means it's a coherent state. So these are called coherent states. They were known way before Glauber. In fact, I think Schrödinger knew them, but Glauber was the one that introduced them and popularized them in the field of quantum optics and showed how important they were. It's rather easy to see that if you build them from the number eigenstates in this fashion, which is the same as here, that they obey this relationship. It's kind of easy to see if you let A act on this guy, you have to work your way through. A doesn't commute with A dagger, so you've got to work it through n times to get over to the right, and that picks up a factor n, because each time you move it, and so that n factorial becomes n minus 1 factorial, and then the extra z here balances that, and you see that this is an eigenstate of this guy. So these are the so-called Glauber coherence states. How do I get rid of that? Just by touching? Yeah. It's rather easy to see that they have coordinate space and momentum space representations, which are now exponentials of quadratic pieces in the complex number Z. And I say Z is a complex number. Okay, it exists as a complex number in the complex plane. And the complex plane that defines Z is our quantum phase space. So it's got a real part, which is X, up to factors, and an imaginary part, which is P. And xp, the real and imaginary parts of this, are our phase space. Okay. If I define the usual uncertainties as delta x, so the expectation of x squared minus the square of the expectation, the square root of that, then one can show that, first of all, that the expectation value of x hat in this state is this factor times zr is the real part of z, and up to a factor √2, which is very important not to get wrong, is equal to x. So x, apart from a factor of √2, is the real part of z. And similarly, p up to a factor of √2 is the imaginary part of z. And one can easily see that these obey this, that delta x and delta p are both 1 upon √2. So they're both identical, and they satisfy the uncertainty principle as an equality. So these are the so-called, the coherent states are the so-called minimum uncertainty states. They are the states that are closest possible to being classical. You can't get any more classical than this because you can't reduce that number anymore because that's the uncertainty principle. The uncertainty principle says it's got to be bigger than that. And these two are equal, and that says basically that the state is an unsqueezed state. So delta x and delta p are the same. The uncertainty ellipse becomes a circle and has a radius of 1 upon √2. Now, very importantly, the overlap between two coherent states, you just work this out, there's no algebra involved, is simply given by this. And the square modulus of the uncertainty is this. Now, z minus z prime modulus squared is just a distance in phase space. So you've got 2 points z and z primed. The distance between them by Mr. Pythagoras is the difference between the x's squared plus the differences of p squared, which is precisely this. And so the overlap is a function of this Euclidean distance. So this quantum phase space, I should have pointed out, is a Euclidean space. It's a flat space. You can lots and lots of extensions of this go off into other spaces, into hyperbolic space or ellipsoidal space. I'm not going to talk about that today because it's not so necessary, but it's very easy to generalize into different spaces. So the coherent states are not orthogonal, and that's because they've been defined to be eigenstates of a non-Hermitian operator. The big question is, are they, however, complete? Because if they're not, there's not much I can do with them. And the answer is yes, they are complete in the sense that they form a resolution of the identity. So this is just like, and the integral is over the entire complex plane. That's what this symbol means. Alternatively, in x and p space, this d2z is just dx dp, apart from this factor of 1 upon √2 that occurred in both of them. And I put the h bar back in here just to be precise. Okay. This is quite easy to prove by taking the overlap of this between number eigenstates. And it's 3 lines of algebra. I'll do a lot of algebra as I go along, but this is so easy. This is an exercise for you guys. So easy to do. So they are complete in this sense. They form a resolution of the identity. In fact, they are massively overcomplete. And I will come back to what I mean by that later. But for me, it's not so important that they're overcomplete. It's important that they're complete in the fact that they have a resolution of the identity. Normally, when we talk about Hermitian operators, completeness and resolution of the identity are the same. They're not here. So after that introduction, let's now start moving into this quantum phase space. Now, if we're in quantum phase space, we would like, the sort of thing we'd like to do is to learn how to move around in it. Okay, how can I get from one point to another? And the usual way you think about moving in a space is either to translate, take a step, or it's to rotate, right? So let's do both of those. Let's do displacements and rotations. Now, it was, as I said, this goes right back to the very earliest days of quantum mechanics, and probably the first and one of the most brilliant founders was Raymond Bishop, who was really a mathematician, was a group theorist. And it was he that introduced this so-called displacement operator, which is an exponential of a linear combination of the operators involved, A and A dagger, or X and P. No great surprise of the exponential, because when you have an algebra, when operators satisfy an algebraic structure, it's their exponentials which obey the group structure. That's completely common in mathematics. Now, what he showed was that this displacement operator, this so-called, I call it now the Weyl displacement operator, has the properties that we desire. Now, it's of the form of an exponential of something which is anti-Hermitian, right? Obviously, if you take the complex conjugate of this, you get back to it. You get back to itself. Now, there are two pieces in here, and these two pieces don't commute. So the exponential of the sum of two things, of course, is not just the product of the exponentials. That's what makes group theory so interesting. And in essence, what makes quantum mechanics so interesting. However, this is particularly easy, because if both A and B commute with their commutator, which X and P do, or A and A dagger do, then you've got this simple formula. And then you can show that this operator can be written with this guy first and this guy second, like this, with this factor, which comes from here, or the other way round, in which case you get the same factor, but with a plus sign. And you can do the same down here. Now, what you can easily see from this relation is that if you let this operator act on the vacuum, this bit of it just gives me 1, right? Because if I expand out by a Taylor series, this is 1 minus Z A dagger plus a half Z squared A dagger. Sorry, A, not A dagger squared. And A acts on the vacuum and gives 0. So it's only the 1 that, when I let this act on the vacuum, that just gives me 1. This guy is what I showed you when it acted on the vacuum, gave you the coherent state. And so this is a way of, and so what you see from this immediately is if you displace the vacuum by an amount Z or by an amount X in the X direction, P in the P direction, you get the vacuum put down somewhere else. So that gives a new meaning to what this operator does. More precisely, what's its mode of action on operators and states? This is just how it acts on the vacuum, but how does it act on other states and how does it act on operators? Because we want to be convinced this is a displacement operator. At the moment, it's just an operator. Now, there's another, probably the most important formula in all of, certainly in quantum many-body theory and in much of group theory. And that says that if you take this similarity transformation of an operator A defined by an exponentiated B operator, you get this so-called nested commutator expansion. I hope most of you have seen that. Do you know how to, you remember how to prove it? Unless you remember the trick, it's horribly complicated, but if you remember the trick to replace B by lambda B, and then just make a Taylor expansion in powers of lambda you arrive at this immediately. So the mode of action on operators is relatively straightforward. In particular, for A, it says that I get A, and then I get the commutator of A with the exponentiated operator, which was ZA minus Z star A dagger. And A and A dagger give me 1, that gives me the next term, and all of the others drop out. So it's only the first term that survives. So this is nice. What it says is the mode of action on the operator A is it shifts me by an amount Z, which is nice. That is a displacement, right? And the same on A dagger, it shifts you by Z star. And if you just take linear combinations, you get the operations on X and P. And it shifts X hat by a scalar X, and it shifts P hat by a scalar P. We'll be interested later of the matrix elements of this guy between momentum and position eigenstates. And by going back to this guy, you rapidly see that that you can replace the exponential in here by this product with this extra factor that sits, and then you can let the X hat operator act this way, and it just picks up e to the IPQ1. You let the P operator act to the left, and it picks up this factor minus IX P1, which is this, and this is the factor that sits outside. You can easily derive, so that's the easy one, the mixed one between a position state on the right and a momentum state on the left. If you want position states on both sides, then you've just got to use some completeness. For example, if you multiply both sides of this equation from the left by this guy here, and this is just the overlap, that's where our normalization came in. That's just 1 upon root 2 pi times this exponential. And if I act on the left with this integral over P1 by this extra state, you see this guy and this guy on the left just pick up the identity by the momentum eigenstates being complete. So that's the relationship here. And this is nice because what it says is, it's exactly what you expect. It says if you let, there should be that parenthesis, and it should be over here. That's D of X and P. I thought I'd proofread carefully, but there's always something. Right? If you let it act this way, it shifts Q1 by an amount X. And in the overlap with Q1 plus X with Q2, they're both position eigenstates, is it says Q2 has to be at the position Q1 plus X. That's normalization of the position eigenstates. But it picks up this extra phase factor. That you would have guessed, that you wouldn't have guessed. Same for P eigenstates. So far this thing is doing just what we want. Of course. Say again, please. That's right. Because they've got the suffix X here. So by definition, this is a position eigenstate. And by definition, because it's got the suffix P here, this is a momentum eigenstate. Yes. No, that's the X that sits in the operator. That's the X that's the Q1 and Q2 are the states. X and P are, I'm now shifting these guys in the XP space. So always, I'm trying to say, always X and P I'm going to reserve for moving around in phase space, and things that I call Q1 and P1 are particular points on particular axes. Yeah, is it clear? Okay, good. Okay, so so far this displacement operator is doing exactly what I want. It's enabling me to move from one point in another on both, and it acts on both states and it acts on operators, and its mode of action we can fully determine from its definition. Now, this displacement operator is the most fundamental thing we can do in phase space, is to move from one point to another. So it's pretty clear it ought to play an important role. And we'll see that it does. Let's first calculate its trace. Now, its trace is quite easy to do. Let's take the trace, for example, let's take it by sandwiching it with position eigenstates. And so the trace with respect to position is just this. And if I plug this guy I have just calculated, I plug it in here, it's already got because Q1 and Q2 are now the same. Previously, it was delta of Q2 minus Q1 minus X, so it's just delta of X. And the remaining integral is just delta P. So the trace of this guy is a delta function at the origin in phase space. And these are the normalization factors that sit there. So it's quite its trace is extremely singular. Let's imagine trying to integrate this. So this is an integral over entire phase space, over both X and P. Suppose we do half integrals over X alone or P alone. These are the so-called marginal properties. Okay, so suppose let's try to integrate it over X first. One immediately sees that that we've got, first off, we've got this. Say again, please. This guy here. This one. This one. Yeah. In this one, in the trace. Do we have a? I know, but that's not. I am doing its entire trace. I'm looking for a marker. Do we have one?
No.
Yeah. Okay. All I'm saying here is that the trace of, let's say, any operator, forget that it's d hat, the trace of any operator by definition is the trace of the operator times the unit operator. And in particular, I can write the unit operator as the integral on dq That's the completeness of position states. Now, the trace of a product of operators is that it's cyclic. And so this is simply the integral over dq, the trace of theta hat q, which is the same as q theta q. And that's all I've done, just by choosing to work with position states to find the trace. The trace is just the sum of the diagonal elements in any orthonormal basis. So this is the orthonormal basis for the position eigenstates. And the sum becomes an integral. Look, in this equation, I have not integrated at all over X and P or P. So this is not an integral over phase space of this trace. That comes later. That comes later. Okay, it's obvious what it is. The integral of the trace is just the integral over a delta function, which is 1. Okay, but let's first do the half, the marginal. Let's integrate over x alone first. So and that gives me this. So that brings me down to here. Now, what my terminology here to try to make it easy for someone that's looking is when I'm doing a string of doing some algebra, I work in brown. So it's not a final result. A final result is always in dark blue. When I'm working, when I've got something in brown, but I want to work on a bit of it alone, I color it cyan. So now let me do the cyan bit in here and the cyan bit in here. Well, that cyan bit is nothing more than an identity operator, and that cyan bit is an identity operator. Okay, so that tells me that the integral that I'm looking for is this remaining integral, and the last bit to do here is simply to do the remaining integrals on Q2, which again gives me the identity, and the integral on Q1, which again gives me the identity. And so what I get, this now should be colored blue, is the half integrated or marginal relation for this is quite interesting. So it's up to a factor of 2 pi. It's the ket state not at p, but at half p. That's unexpected, I would say. And the bra, and then it's multiplied by a bra because this is an operator, and that's the state at minus a half p. This is not totally expected. Why have we got p and minus a half, or half p and minus half p? Well, we've got it because of the algebra. But I don't think many people intuit this the first time they see it. The same thing you can do by integrating on p space, and you get this x space projector. Now, p goes to minus p, or half p goes to minus half p, half x goes to minus. That's what parity does. Parity changes the sign of x and p. So if I introduce the so-called parity operator, whose mode of action on x states is to reflect them, and the mode of action on p states is to reflect them, then I can say that this guy, fully integrated, if I want to just put this back to a plus a half p, I put a pi 0 between them, which is this so-called parity. I put a 0 on here because it's the parity operator reflections about the origin. X goes to minus x, p goes to minus p. And then if I integrate these one more time, which I think is the question you were asking in the very first place, then I get the parity operator. So the integral of this guy over, it's rather remarkable. Each one of these d operators shifts you by an amount, and if you integrate over all of them, you rather expect that you might get the identity, because you shifted to z, another one shifted you to minus z. Whichever one you did, you've got another one. But in fact, you don't. You get the parity operator. There's no arguing with this. This is correct, but it may not be intuitive to you. It's not only the parity operator, it's 2 times the parity operator. And that's because what remains here is minus a half. And when I want to integrate, when I use completeness here, I've got to replace p by half p by 2p primed. Said that the wrong way round, and that introduces this extra factor 2. So this is our first Why is it half? just is. I mean, that's just doing the algebra. Yeah. I'll come back to it. If you allow me, let's come back to that and ask, why didn't we get plus a half p here? That's a really interesting question. And the deal is, this guy doesn't do it, but there's another operator that does, and that's the guy that I'm going to introduce next. So give me 5 minutes. Okay. All right. Now, you see, all of this stuff is based on really simple ideas, really simple operations. But, you know, when you pile up a number of those steps, you're not totally clear which direction you should be moving. It's like moving in a maze, right? It's easy to undo a first couple of steps or take the first couple, but rapidly you wander off into terra incognita. This is not a difficult operator, but it's got a remarkable property. As a remarkable property, it was due to this very clever fellow Moyal at Cambridge that says if you take the operator D dagger and you take the operator D and you sandwich them, this alpha, gamma, beta, and delta here are arbitrary states, totally arbitrary states. And the deal goes this: if you take this for any states, you make nothing about these states at all, you get this remarkable formula. And it is quite remarkable because this alpha now comes over to this delta and this beta comes over to this gamma. This is the proof of it. This is the proof of it. It's in brown, and I'll gladly go over it, but probably, I mean, this you can look up later. I mean, these slides will be available. It's not difficult to do from the formulas that I've already done. I can go over as much of this algebra or as little of this algebra as you really want. I'll go over quite a bit of it. This is not difficult to do. It just, all you have to do is, we don't know why do I call this minus x and minus p? Yeah. Any state you like, absolutely any. They can be a part of an orthonormal set, they can be coherent states, any state you like. That's what makes this considerably, really a remarkable formula, I think. Basically, the way I'm doing this, I start with minus x and minus p here, because this guy with minus x and minus p is exactly the same as d dagger with plus x and plus p. And that's the first bit that appears in this formula, right? So the d dagger of z is the same as d of minus z, just by definition. Okay, you can rapidly see that. So we don't know this between arbitrary states, but what we do is we just keep sandwiching complete sets of states between to get something we do know. For example, we know the position, we know the matrix elements of this guy between position eigenstates. So let's insert complete sets of position eigenstates here and here. That's all I've done here. This guy I know because I've just proven it to you. I bung it in, and this is the relation that you get at the end of it. Okay? So this is a result that we will use, and it is incredibly powerful. Yep. Correct. 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 Absolutely so. Okay, so that's displacements. So we've learned how to walk from one position in phase space to another. What about rotations? Those are basically the only things I can do, the only elementary things I can do in phase space. Any journey in phase space is a combination of rotations and displacements. Let me, no great surprise, the rotation operator is the exponential of I theta times the number operator, A dagger A. I say that blithely, and lots of you will nod because you've seen that, but let me prove it to you. Okay. What is the mode of action of this on these operators? Well, let's take a dagger first. So take a dagger, R on the left, R dagger on the right. That gives its mode of action. It's this. Now just plug in the nested commutator expansion. Okay. Now use the fact that this commutator, a dagger with the number operator, just gives me, from the basic commutation relation, it just gives me minus a dagger. So now every term in here picks up. They're all the same. Every one of these is the same, and I get an extra minus sign. So the extra minus sign I get in here takes that in the sum, turns that minus into a plus, and this, of course, is nothing more than e to the I theta. So its mode of action on a dagger is to multiply it by just a constant. In fact, a pure phase factor. So, and take the complex, the Hermitian conjugate of that gives its mode of action here. So if I just take the Hermitian conjugate of RA dagger R, I get RA R dagger, and that just picks up e to the minus I theta. X and P are just linear combinations of A and A dagger, X hat and P hat, and that's what you get. Well, that's a rotation, right? X goes to cos theta X plus sine theta P. P goes to minus sine theta X plus cos theta P. That is why it's a rotation. Special case of this rotation operator is the parity operator. If I put theta equals pi, so that guy is the parity operator because its mode of action on X is to change it to minus X. Just plug in here, theta equals pi, that term disappears, and the cos just becomes 1. And so we, sorry, the other way around, the cos becomes, yeah, okay. So the parity operator is a square root of the identity operator that is just a rotation by pi in phase space about the origin. So now we've constructed this operator. Another very interesting special case, so about theta equals half pi. So that does exactly what you expect. So I'm going to call this, for reasons that will become immediately clear, I'm going to call this the Fourier operator. Why? Because its mode of action on X is to change it to P, and its mode of action on P is to change it to minus X. Here's X, and here's P. Rotate by pi upon 2. So look at my right arm. X has gone to P. P has gone to minus X. So that's the rotation, but that's what Fourier does, right? He says you Fourier transform, you turn P to X. The inverse Fourier transform comes with an extra minus sign. So this is a way of doing Fourier analysis. There's a general case where theta is not pi by 2, but is an arbitrary. And this is very not known by many physicists, and it's not even known by many mathematicians. But this is fractional Fourier transforms. And it turns out basically what you are doing is when you rotate by an angle theta, let's say a position state which is position along the x-axis, you now rotate it to a position along a theta axis, not necessarily pi by 2 now. And there is a relationship to invert, which involves this guy. Much more complicated than e to the IPQ. It becomes e to the IPQ if theta is equal to pi by 2. This is very important in things like, actually in signals analysis, things like this. fractional Fourier transform is known in that field and not very many others. More or less an aside here. Now, let's revisit this parity operator about the origin. And its trace now, we've got this relationship. I've already proved this one to you. The integral over all phase space of the trace of the displacement operator is the parity operator. But if I now take I know the trace of this guy, and I get this relation. So the trace of the parity operator is a half. Again, that's rather strange. You might have thought, if I asked you to guess what it was, you probably would have said it was 0. It's certainly what I would have guessed, because the same reasons as you thought that the displacement operator was going to integrate over all space to give me 0. But that's the mathematics. Now, I could also evaluate this trace. This is interesting. I could also evaluate this trace in the number eigenstate basis. So let me sandwich this guy between number eigenstates and sum up diagonal ones. That's the definition of the trace, sum of diagonal matrix elements. And what do I get? Well, this guy is -1 to the power n. That's easy. That's just the number eigenstates. So this is a series that goes 1, -1, +1, -1, +1, -1. It's clearly a divergent series. If I stop at the first term, I get 1. If I stop at the second term, I get 0, 1 minus 1. I go further, I get 1. So what's the if you take this completely literally, you don't know what you're going to get, right? It's either 1 or 0, but the mathematics, the rigorous mathematics says you get a half. And that you can find, so this equation is completely compatible with this. It just so happens if you try to work in this basis, you will get an answer that you don't quite know how to interpret. What you actually have to do is to say that we're not just rotating by an amount by pi, we're going to put an epsilon in here, and then you find that what you actually get is a one-sided limit. So the mathematics in here can be subtle. And you have to be careful with things that you are doing, because you may get answers if you work in a particular basis that you can't quite interpret. But what often happens, you work in another basis and you get a definite result that you can interpret. You're always working on the edge of singularity with these things. So it makes what makes the mathematics particularly interesting. Now, this will come back to the question that you asked. Now, a very important role is played by this so-called displaced parity operator. So what I'm going to do is I'm just going to take my parity operator at the origin and I'm going to displace it. So that puts a d on the left, d dagger on the right by an arbitrary z or an arbitrary x and a p. What do I get? I call it the parity operator at the point xp. So this is just my definition of what this guy is. Its property is that it squares to 1, so it's also a square root of the identity, and it's Hermitian by definition, because pi 0 is Hermitian, so pi, this arbitrary pi is also Hermitian. It's very easy to see that its action on position and momentum eigenstates is this. You might ask, why do I get this peculiar combination? Well, basically, what you are doing in here's x, here's p. Let's look at this guy first. Basically, what pi does is it says set up a mirror at that point in space. So suppose I put my mirror here at the point x. So that's the x in here, and I want to find what its mode of action on a state q1 is. Well, Q1, let's say Q1 sits here. And if I reflect it across this mirror, it goes to here. So what's that position? Well, this distance is Q1 minus X. So therefore, this distance is Q1 minus X. And so what is that guy? What is, let's call that Q1 primed. So Q1 primed is X minus Q1 minus X, which is precisely that guy. So it does what you think it does. It puts up a mirror at that point and reflects. And it does the same in P space. So instead of putting the mirror this way, I put the mirror this way. So it's doing what I want it to do. It's very easy also to show that its action on position and momentum operators, it does the same thing. It first changes the sign of the operator, that's the parity bit of it, and the displacement bit of it takes you the same argument I've just done. This displaced parity operator is supremely important. You might not have otherwise guessed this. Hermann Weyl guessed it in 1927, and probably it took another 50 years before it was rediscovered. And these are alternate forms for these guys. Now, I can rewrite this last equation, and this factor of 2. Remember where that came? That factor of 2 was very important, and it's already appeared before. If I write that last equation in terms of x and p instead of z and z star, and x hat and p hat instead of a and a dagger, I get this simple relation, which just comes from plugging in here. And so there it is. And you put the factors together, and just without the displaced bit of it, the x hat and the p hat here just give me back the d operator with this extra phase factor. Well, that extra phase factor is just nothing more. If you stare at this just says that this guy is the 2D Fourier transform of this guy. Right? This is just two-dimensional Fourier transform. Well, I can Fourier invert. And so this says the displacement operator is actually nothing more than the Fourier transform of twice the parity operator, and vice versa. Not things that you would necessarily guess, but very important for later developments. Banu, when should I stop? Banu, when should I stop? I can't hear you with your mask on, I'm afraid. Okay, so let's start to wrap up then. So in exactly the same way as that displacement operator satisfied a relation which is exactly the same, but there I had a d dagger and a d, and it gave this same thing. I can do exactly the same for this displaced parity operator. Valid for arbitrary states. It's got this very important factor of 2 in here, and I will make use of these two relations when I continue to introduce the so-called Wigner function and the Weyl function. These operations, this at the moment is just operators, but these lie at the heart of phase space distribution functions. So that's why I'm going over this basics fairly thoroughly. I suspect a lot of it is familiar to some of you, but probably all of it is not familiar to all of you. And I will, let me just see where, let me finish because this answers your question. We could, just as we looked at the marginal properties of the displacement operator, and it had this half p ket minus a half p bra, we can do exactly the same thing for this operator. And this guy does exactly what you want it to do. It gives you x and p and p. So this operator, when I integrate over p space, it projects me completely. This is the projector onto x space. And on integrating over x, it projects onto p space. You might have thought at first sight the displacement operator was going to do that, but it doesn't. It's this guy that does it. And it's this guy is actually even more important than the displacement operator because of this. Although in reality, they are both very much the same. This guy lies at the heart of the Wigner distribution. The other guy lies at the heart of the Weyl distribution. And that is what I will pick up next time. And furthermore, if I then integrate either one of these over the other, so integrate this one on x, again, use completeness here, with the usual factor of 1 upon 2 pi in here, this gives me a half. That basically says that it's 2 pi that is the operator that's important, twice the parity operator, not just the parity operator. And the reason it's twice is because the trace of it is a half. And typically the most fundamental operators have trace of 1. And so it's the twice the parity operator that has the trace of 1. That brings me nicely to having set up all of these moving around. And now we're at the point where we can introduce phase space distribution functions and start to get onto the work, which, for example, earned Glauber the Nobel Prize in whenever it was, 2005. Which probably should have been shared by Glauber and your very own George Sudarshan as well, but that's another story. So let me stop there for today and pick this up again and finish it off tomorrow. Were all the questions answered as we went along, or does anybody still have any questions or queries? Okay, thanks.